Hello, quantitative methods class. For today, we're going to talk about the new statistics. New in quotation marks because many of these are not necessarily new. We're going to talk about different approaches to inferential statistics other than null hypothesis significance testing. We're going to talk about some problems with null hypothesis significance testing and ways that we can combat these problems, and maybe look at some approaches that might be better than null hypothesis significance testing, or maybe to use in conjunction with the more traditional ways of doing inferential statistics. So we will look at problems with null hypothesis significance testing. We will then look at confidence intervals. What are they? Are they useful? And then we will look at effect size, a very important concept. We're not just caring about is there a difference or is there no difference? How large is that difference? That seems to be a very important practical question that null hypothesis significance testing neglects. What is the size of that effect? So that's something that we're going to be very interested in. And we focused a lot on type 1 error, okay? The probability of us rejecting the null, and yet the null hypothesis is actually true. But how about the other side of the equation? How about for type 2 errors, where we fail to reject the null hypothesis when in fact the null hypothesis is wrong? Okay, we haven't spent a lot of time focusing on that. So we're going to tackle the issue of power and how that's related to type 2 errors. All right. What are problems with null hypothesis significance testing? First of all, the logic seems very counterintuitive, and the logic is hard to understand. Okay, we're providing evidence for the research hypothesis by rejecting the null hypothesis, by seeing if the null hypothesis fits the data, and if it doesn't fit the data very well, then we go to the research hypothesis. Okay, a little bit confusing for many people, okay? And probably at this stage, you might be a little bit confused about that as well. Okay, so null hypothesis significance testing has been the dominant force in biology research, economics research, psychology research, sociology research, in many of the sciences. Any science, any discipline that uses inferential statistics probably looks at things through the eyes of null hypothesis significance testing. In fact, pretty much all the papers that are published now use this approach when analyzing their data. There are a few exceptions, but they might do something fancy and then still have the null hypothesis significance testing. That doesn't mean that this way is correct. It also doesn't mean that this way is right. There are many problems with null hypothesis significance testing. Let's talk about 3 misconceptions that people typically have when they first learn about null hypothesis significance testing. All right, we find a significant result. We find a statistically significant result. We make the assumption that this effect is important, and that is not necessarily the case. All right, a significant result, we're inferring that in the population there's a mean difference, but we're not necessarily care about what is that mean difference. Is it a small difference? Is it a large difference? It might not be of any practical importance. Suppose we were to conduct a study and we're trying to see if there's any differences in aging on memory. And we do this study and we find out that yes, there's a difference in memory. If you're trying to recall information, there's a difference between older adults and young adults of 1 out of 100 items. So let's say that the young adults recall 60 items and the older adults, the population mean is 59. Okay, so yes, there's an age difference, but it might not matter. All right, and it might not be that important. I mean, maybe we say, oh, older adults are slowing down, but it's a difference of 1 millisecond. Who cares? Okay, it is a difference, but practically speaking, that shouldn't matter that much. We should not necessarily be concerned about the slowing during aging if that is the effect. All right, maybe there's a difference between men and women and how they do on English standardized testing. Maybe women outperform men in English standardized testing, which typically is the case. But is it a big effect? Should we be concerned about this effect? Or is it a minute, itty-bitty effect that it doesn't really matter that much? Okay. The effect might not be of practical importance. So suppose I were to come up with a new way of teaching students. Okay. Instead of teaching students this one way in a classroom, I say, well, you can completely do away with all of the work that you've already done, and you can implement this new way of teaching students, and it will change their standardized testing scores from a 500, or maybe let's use this example here, from a 50 to a 52. And that might not mean that much, okay? That might be more work than it's actually worth, all right? How about if we are a company and we have a new test that might predict employees who's going to be a successful employee better? But if it only ups the prediction a little bit, why spend all the money, spend all your resources purchasing that new test and implementing that new test when it really doesn't improve the prediction by a ton? Why change the way that your class is working if it's only going to improve things a little bit? Okay, so a statistically significant result doesn't tell us if the effect is important. I've mentioned this to you guys before, but I'm mentioning it again. It's a big thing to wrap your hand around. And here's another thing. With enough subjects, with a large enough sample size, any difference will be significant. Okay, any population mean will be significant with enough subjects. So if we were to run 20 subjects, we might not find the effect, but if we run 10,000 subjects, we will see a mean difference. We will see a population mean difference, okay? When you have that many subjects, pretty much any difference will be significant. That doesn't necessarily mean that that difference is important, okay? So that's one popular misconception. All right, let's look at the other foot. So if we fail to reject the null hypothesis, if we retain the null hypothesis, this does not mean that the null hypothesis is true, okay? Sometimes we just don't have enough subjects, okay? There might be truly a mean difference here, but we don't have enough subjects to find a statistically significant result, okay? To use a term that I'm going to use later, we don't have enough power to find a statistically significant result, okay? Very rarely when we're looking at population means, is there going to be absolutely no difference? Now, those population means might be very similar to one another, but very rarely are there going to be absolutely zero differences. All right, so just because we have a non-significant result doesn't mean that the null hypothesis is true. And this is why we say that we can never really accept the null hypothesis. All right, it might be the case that the difference is itty bitty, tiny difference between the population means that we just don't have enough subjects to see or to get a statistically significant effect. All right. Another popular misconception is that if we find a statistically significant result, if we reject the null hypothesis, this means 100% of the time that the null hypothesis is false. And this is not true either, okay? Remember, we set the type 1 error rate, we set alpha to be 0.05. So if the null hypothesis is true, there is a 5% chance that we are going to reject the null hypothesis when in fact it is true, okay? This is why replication is so important in psychology, all right? If we find something, we need to make sure that other researchers are finding it as well, okay? And if we get multiple people replicating it, it's probably safe to say that that's something important, okay? We don't want there to be many papers out there where someone says, hey, I rejected the null hypothesis, I found this really cool effect, when in actuality, it is a type 1 error. This is why many publications require you to perform the experiment twice, or maybe a few more times, to make sure that that effect replicates, okay? As you get into the higher quality journals, they are wanting to see that these effects replicate across a series of studies. All right, so these are all popular misconceptions. All right, and they are problematic, so hopefully you will not make them, but plenty of people who first learning statistics make these improper assumptions when doing null hypothesis significance testing. All right, yeah, I'm just showing here are that we always have, no matter what, some level of type 1 error. We always have some level of type 2 error. There's never a situation in which we can be 100% confident when we're doing any inferential statistic. Okay, so those are misconceptions of null hypothesis significance testing. One problem with null hypothesis significance testing is that it leads researchers, it leads statisticians to dichotomous thinking. Dichotomous thinking is you either think that there is an effect or there isn't an effect. There's no in between. All right. Other examples of dichotomous thinking is this person is completely moral, completely good, or completely evil. People are not in the middle. All right. So doing null hypothesis significance testing, there is either an effect or there's no effect. And this is problematic because there's various shades of gray in statistics. Okay. So in many instances, we're so caught up in trying to say that there is an effect and that's wonderful and we should get all of our studies published and we need to cheer and all of that's wonderful, or we don't find a significant effect and our research is unpublishable. All right. And that's a really dangerous mindset to have. Okay. So many times we are trying to see if there's an effect, but we're not determining the size of that effect, something that's more of practical importance. All right. So here we see two different distributions of the population. Okay, here at the bottom, we see a huge or a larger mean difference. And here we see, as we go up, smaller and smaller population mean differences. Sure, there is a difference in here in this first graph, but it might not be of any practical importance. Okay, so when we use null hypothesis significance testing, it forces us into this binary type of thinking that there either is an effect or there's not an effect. And I mean, when we calculate our p-value, okay, if we have a p-value of 0.049, we reject the null hypothesis and everything is good and glorious. If we find a p-value of 0.051, we fail to reject the null hypothesis and everything is bad and we can't publish. Is there really that big of a difference between these two p-values? Okay, no, there is not. So this dichotomous thinking is very very problematic for us to have in statistics. All right, there really isn't that much of a difference between a p-value of 0.049 and that of 0.051. Okay, so one major problem of null hypothesis significance testing is that we neglect the effect size. Okay, we are led to there's either an effect or there's not effect, and there's nothing in between. We can't process maybe a moderate level of evidence that the null hypothesis should be rejected. Okay, so that's one major problem. Another major problem is there is, and this isn't necessarily null hypothesis significance testing's fault, it's just the way that science institutions work. There is a thing called publication bias. Okay, sometimes it's called the file drawer problem. That was a term coined by Rosenthal. So a publication bias, or the publication bias, is the bias both with researchers and editors and reviewers that if a statistical finding is significant, we publish it. If a finding is non-significant, we reject it. All right, and that's hugely problematic for, so let's say that we just happen to find that cognitive training improves intelligence, okay? Heck, it could even be a type 1 error. We're going to accept that publication and it's going to be published and it's going to get a lot of press. However, if you find that cognitive training does not work, well, that's not as cool of a story. So you might have more trouble getting that published. So if you peruse the literature to see if cognitive training works, all these studies are saying, yay, it's wonderful, it's glorious, when in fact, maybe there's tons of studies that fail to find any difference, but they just haven't been published. All right. So editors of journals want the journal to do well. They want the findings to be exciting. So they are going to be biased in a certain way to accept papers that find statistically significant effects, and they're more likely to reject articles that don't have as cool of findings. All right. How about for editors? Or not editors, sorry, talking about reviewers, people that are reviewing the paper. Let's say that there is some ambivalent evidence, okay? Some of the statistics, some of the analyses in the paper show an effect and others do not. Well, a reviewer might say that that's inconsistent, and if it's inconsistent, it doesn't belong in the paper, and all of a sudden you're trying to be honest, and the paper is not published, and you can't find a space for it, okay? But many times the evidence to support something is ambiguous, right? That doesn't mean that the data doesn't belong there. Okay, it just means that we have to be a little bit more cautious when we interpret the findings of the paper. Many times the reviewers of a paper might be somebody that we're arguing with that might have found positive results, found statistically significant results, and they might be very combative for somebody failing to replicate their study. Okay, I can list hundreds of examples of this where somebody finds an effect and everybody is super interested and this is a super neat study, and yet in the years following that paper many people try to replicate it and they can't find that same effect, and the original author, it gets very defensive about everybody not finding their really cool finding. So they might act as a reviewer and try to squash those papers as much as possible. This is not good. This is not a good practice, but it does happen. Okay. And maybe it's the case that the actual person conducting the study might not publish it. They might stick it in their proverbial file drawer, okay, never to see the light of day. If you have a fun finding and you find a significant difference somewhere and your career is based off of that finding, let's say that you've conducted future studies and don't find the same results. Ooh, might be a blow to your ego. It might call into question all of your previous findings. So you might just never let those studies see the light of day, even though those studies are very important to get out there. All right. So just to kind of show you the massive problem here, here we have a paper from Science. And here we're looking at 221 social science experiments, so things in sociology, things in economics, things in psychology. And what happens with the paper if they have strong results, okay? Maybe all of their statistical tests are significant. Maybe there's some mixed results, or maybe they find no effect whatsoever. Look at the fates of these. If we find a significant difference, if we reject the null hypothesis, it's very likely that we write up the paper and then we try to publish it. If we don't find any significant differences, we are more likely to not write that up. And even when we do try to publish these results, many times they're going to be rejected. Many times they're not likely to see the light of day. This is hugely problematic. And null hypothesis significance testing leads itself to this dichotomous thinking. The results are good if the p-value is less than 0.05. The results are bad and should never see the light of day if the p-value is above 0.05. Okay, not good, not good. Let's talk about some other problems here. So along these lines, researchers, to get their paper published, because to be a professor, you've got to get things published. That's how you get tenure. Getting things published helps you get grant money. It helps you getting notoriety. So you want to get things published. Sometimes that might lead you to cut corners. Sometimes this might lead you into inappropriate data practices, unethical data practices, to try to get your study published, to show a significant result, because that's what everybody wants to see. They want you to reject the null hypothesis. They don't necessarily want you to retain it. So there's this notion of researcher degrees of freedom. a degree of freedom, which we'll talk about actually in the next module. These are things that are free to vary. And there's many decisions that you make as a researcher that are going to lead to an increased chance of us rejecting the null hypothesis. And many of these things are inappropriate for us to do, but we might try to do them to cut corners to make our data look better and more publishable than they really are. Now, of course, the hugest problematic thing to do is to fabricate one's results. And there has been some evidence of this in psychology and in other disciplines, okay, where a researcher just says, okay, I don't want to even conduct this study. I'm just going to fabricate what the results are. But many times we're specifically talking about researcher degrees of freedom. These might be things that the researcher might not know is really bad or unethical. It might be things that are somewhat shady. All right. So let's talk about a couple of these and how they're problematic. One is determining when to stop the study. Now, when you were conducting a research study, you make a decision, I want X number of subjects, and then when you're done, you stop. You don't look at your data, and then when the data looks good, then you stop the study, okay? Some researchers might do this. They could constantly look at the data and then wait till it looks really good and stop the study right there. Whereas if they would have ran 4 more subjects, the data might not have looked as good. Okay, so researchers might be searching their data, and then when it looks good, they stop collecting data. This is problematic. You should not analyze your data really before the study ends. You should wait till after the study ends to analyze your data. I mean, you want to look and make sure all the data is being calculated correctly, but this is not a good practice of looking at the final results and running as many subjects until you find a significant result. Not good, not good. Okay, another problem is sometimes researchers might conduct many statistical tests and only report the ones that have a significant result. Or maybe there is a problematic statistic that would call the study into question. Maybe there is a confounding variable that when you control for it, all of your results go away. Now, you might selectively leave those analyses out of your paper because it leads people to kind of question your results. And as I've mentioned before, reviewers of a paper, if they latch on, if they sense any data that's contradictory, they might just reject your paper outright. So some people are just going to try to hide that data so that they can get away with reporting this significant finding, making their data look better than what it really is. Okay, this is problematic. You want to make sure that you show your data with all the freckles, with all the blemishes, and don't try to hide anything. Now, sometimes papers will make sure that, or try to make you report less information as opposed to more information, and that's really problematic. But you try to get all of the analyses that you conduct, all the important ones out there, at least in the paper or maybe in the supplemental materials online. All right. How do you deal with outliers? Do you remove all the outliers from your data? Do you take all the outliers that are 2 standard deviations above the mean and just set them to 2 standard deviations above the mean? All right, there's many different ways that you deal with outliers. What's problematic is if you do the outlier analysis and look at the data before and afterwards and pick which one makes the data look better and then go with that one. That's when you run into a problem. You need to decide before you begin your experiment how you want to handle outliers. Do you want to remove them? Do you want to set them to a particular number? Maybe you don't care about outliers, but you want to make this decision without looking at the data. Okay, you want to make this decision without looking at the data because you might be tempted to select the option that makes your data look the best. And again, that's not ethical. It's very problematic. Okay, which control variables do we look at? Maybe it's the case that if we control for one specific variable, our entire analysis goes away. We don't find a significant result. Our result is a function of maybe a third variable problem. Okay, maybe this one confound completely explains the findings that we have. Some people might try to leave that analysis off. Again, that's problematic. Choosing a statistical analysis to provide a more favorable outcome. There's multiple ways to skin a cat when it comes to statistics. We can run many different analyses to try to answer the same question. Especially the further you get in statistics, there might be multiple ways to kind of get at the same kind of research question or research hypothesis. One thing you could do is do all of the different ways and then see which one is better and then report that. But again, that's cheating. That's making your data look better than it really is. And that's going to lead to an increased type 1 error rate. And all of these, okay, lead to an increased type 1 error rate. And that's why they are so problematic. Okay, if the null hypothesis is true, we only want it to be the case that 5% of the time we reject the null hypothesis. But if we do all of these practices, okay, the number of studies out there in the published land that are complete BS is much higher than 5%. Okay, so these are things that we want to avoid, definitely. Two specific researcher degrees of freedom that we're going to focus on because they've been a huge topic of debate in the past decade or so. One is p-hacking. P-hacking is where we use our researcher degrees of freedom to get our p-value lower than 0.05. So we might be using checking different ways of doing the outliers, checking different control variables, maybe reporting some analyses, not reporting other analyses. We do all these certain things so that we get a p-value of lower than 0.05. So we can say, hey, I rejected the null hypothesis. I have a statistically significant result. If we look at papers actually that have been published, let's start off with this thing. Okay, so here we're looking at papers in a popular psychology article, Psychological Science. And these are the reported p-values. Notice the jump up between 0.055 and 0.05. Okay, so we're kind of going down, but there's a huge drop right here. It seems that people are more likely to report p-values that are right at that threshold of 0.05. We can actually see this here in this graph as well. So these are the p-values in many articles in psychological science. And notice where the outlier is. There's a lot of p-values that are right at the 0.05 level. It's almost as if there were a number of articles that were on the other side of the p-value, okay, and the 0.06 range and the 0.055 range, and somebody has changed them in certain ways, did a different analysis to get it below that threshold. And null hypothesis significance testing leads us to try to make these decisions. Okay, it leads us to really want to go on the other side of the p-value. Okay, let me repeat that. Let me explain that more. Null hypothesis significance testing leads us to try to get below that threshold, below that alpha level, which is 0.05 for psychology. And this is very problematic because it leads us to do some shady things to try to find a statistically significant result. Whereas if we were okay with something in the middle, okay, if our p-value is 0.07 and we could still get it published and just had to be a little bit cautious about things, we wouldn't feel this need to change things to make the data look better than what they really are. Okay. Another researcher degree of freedom is called harking. Harking is hypothesizing after the results are known. So one thing that you might do is You conduct many statistical tests and you see which ones look the best, and then you change your research hypothesis to match the data that you found. All right. I was trying to find a great way to explain it to you guys, and I came across this image on the internet, and it's great. Okay, someone's randomly shooting at a wall or a fence, and then this guy, after the fact, is drawing the bullseye, so it looks like he did a great job of hitting the target. Okay, it's kind of what harking is all about. Okay, this is a image about some of the researcher degrees of freedom, some of the problems that occur in research. Harking right here, this is where we interpret our data, we look at our data, and then we specify the hypotheses based off of the way that the data looks. Okay, so great example of this for where you guys are at right now in the class. Do you decide to do a one-tailed test or a two-tailed test? Well, if the data, we look at it and it's in one direction, well, why don't we make a hypothesis that the direction of the mean difference is in the way that the difference actually is when we conduct the study? This is very problematic. Okay, let me give you a good story about this. All right, give me 1 second. All right, so we've got, what's this guy's name? Last name Hooker. Not important because he did a very bad job with some of his statistical analyses. So in 2014, the CDC published results of a ton of data looking at the question of, do vaccines cause autism? All right. As you probably know, this is a huge area of contention, and many parents over the past 20 or so years have stopped their children from being vaccinated. However, the data is very suspect. There's very little evidence that supports this claim that vaccines cause autism. And if you look at the data in its entirety, there really is no data that supports the idea that vaccines actually cause autism. So the CDC published this huge data set that shows absolutely no results where vaccines cause autism. But this guy, Brian Hooker, that's his name. Brian Hooker thought the CDC might be trying to only selectively report some of their results. So he goes on this huge venture in the CDC's data. And he conducts all of these different statistical tests. Is there a difference in men versus women with whether or not vaccines cause autism? Maybe it's the case that it only causes autism in men. So no, he doesn't find that. So then he breaks it down by ethnic group. Okay, maybe it's the case that only Caucasians have. Is there a relationship between vaccines and autism? So he does all of these different statistical analyses. And he ends up finding one, okay? And of course, if you do enough statistical analyses, you're going to find a significant effect. That's just the way that null hypothesis significance testing works, okay? If we do enough statistical tests, we're bound to find something. And that's what Brian Hooker ended up finding, okay? He found, when you look at the CDC's data, that if you are a Black male, okay, vaccines seem to cause autism, okay? But what this turned out to be is a type 1 error. Again, if you break down enough statistical tests, okay, if you run enough statistical tests, if you keep breaking down, okay, well, we've got white individuals. Okay, now let's look at the guys. Now let's look at if the children are born this certain year to this certain year. If you do enough of them, you're bound to find the result that you're looking for. Okay, and of course, after he published this, and people made the same argument that I'm making, people have tried to replicate this finding, the same if it's the case that Black male children are likely to get autism if they're vaccinated. This effect doesn't replicate whatsoever. It was a type 1 error. But it kind of shows you the problem of harking, okay? Of hypothesis. If you know the results, you keep searching the data, you're bound to find something. You're bound to find something interesting. And that's problematic, okay? It's very problematic. So again, I'll do the example of one-tailed test versus two-tailed test. Do you decide to do a one-tailed test or do you decide to do a two-tailed test? This is a decision that you have to make before you look at the data, okay, preferably before the experiment even begins. All right. You could, maybe with researcher degrees of freedom, conduct a one-tailed test after you see where the mean difference is. If the mean difference is this group is higher than this other one, is the mean difference where the second group is higher than the other one. Okay. If you do this, okay, what you're essentially doing, all right, is instead of putting 5%, okay, all of your rejection region on one side, we're splitting that rejection region into two equal parts, so it adds up to 0.05, which is our alpha level. You're essentially putting that 5% on both sides of the distribution. So what is your actual type 1 error rate? Well, it's not 0.05. It turns out that it's actually 0.10. So this inflates the type 1 error rate. So 1 out of 10 times, if the null hypothesis is true, we're going to reject the null hypothesis, okay? And that is not good. That is cheating. So we should not do that, okay? So those are some major problems with null hypothesis significance testing, but you probably want to know, how do we fix these problems, all right? How do we solve these problems with null hypothesis significance testing? And this is an issue that has not been solved, and there are some pretty heated debates over what is the best thing to do. Now, some people say, well, all the other ways are complicated. I learned null hypothesis significance testing when I was in school, so that's what I'm going to stick with. Okay, but other people have different ideas about what's going on. Okay, so what are things that we can do to deal with the problems of null hypothesis significance testing? Okay, what I'm going to be talking about in this module are the quote-unquote new statistics. And again, there's nothing new about these except for maybe meta-analyses. These are a new branch of statistics that have really been around only since the 1980s, 1990s, when they became popular. This is a big, important book that's been published on statistics, and a lot of journals have gone with the suggestions of Jeff Cumming. He argues that instead of reporting p-values, instead of focusing on p-values, that we talk about the size of the effect, not if the effect is statistically significant or not, but is it a large effect? Is it a small effect? Okay. Instead of just reporting what the sample mean is, to report confidence intervals. So maybe it's the case that within this interval between this value and this value, there is a great likelihood that the true population mean falls in this interval. So instead of doing a single point estimate that we think that the true population mean is this, we give an interval. And there's many advantages to those intervals that we'll talk about here in the next video. Lastly, but not least, is meta-analysis. With the meta-analysis, this is a statistical technique where we take the results of many different research studies that are studying the same topic, and we combine them together statistically. Okay, so this study has 60 people. This study has 90 people. There might be some differences in the studies, but let's have a huge analysis where we combine the results of all of those studies. Okay, meta-analyses can help us answer many important questions, and we'll see what those are. So these are some things that we are going to talk about. I'm not going to teach you how to do meta-analysis because that is way above our pay grade in here. But we are going to talk about confidence intervals and effect sizes and how to interpret those, because those are very important. So there's one branch of statisticians that say, well, we need to go with these new statistics. Okay, we need to make sure that we report confidence intervals, effect size, and conduct meta-analyses, and use them in conjunction with traditional null hypothesis significance testing. And we see that this approach has gotten a lot of popular press. A lot of people like the ideas of Jeff Cumming. Another branch of statistics that people have argued for are Bayesian statistics. Now, think of Bayesian statistics, or people that come from a Bayesian perspective, kind of like Mac people. That's how I view them. Okay, is and this is my bias. Okay, is a Mac computer better than a PC? Sometimes with some things, yes, but the Mac is definitely the trendier option. That's how I kind of view Bayesian statistics. Is it truly better than null hypothesis significance testing? Not really, but it's very trendy right now, and a lot of people are very interested in Bayesian statistics and Bayesian estimation. So what is Bayesian statistics? Well, I'm not really going to teach you this because, again, it's above our pay grade. I just want you to know that this is the next hot thing in statistics, but it has to do with accounting for prior results. So if we are trying to replicate a study, okay, we weight our analysis of that study by all the previous people that have conducted a study similar to that one. So we look at the prior distribution or the prior results of previous studies and use that to influence the statistics that we are doing. Okay, here is a Bayesian statistic book that I actually really like. Krushke is a wonderful author, and there's puppies in the book, so you know, how can it be bad? So some other ways that we can deal with the problems of null hypothesis significance testing. One is registration. And registration, this is where we say how we're going to do the study and we commit to it. Before we even begin the study, we say we're going to run 60 people. This is how we're going to do the analyses. We write all of that up and we put it some location that people can keep us honest about it. Okay. Then after the study is done, we adhere to the rules that we've already set. So we are not able to use those researcher degrees of freedom that we have talked about. Okay. Registering studies is a very good principle to use, and I strongly support that. Okay. So you could use registration of studies to help get rid of some of these problems. And the last thing here is just sense. Okay, kind of like common sense, but I guess it's not that common because it has to do with statistics. Use your research sense to know what to do when you're doing the analyses. Okay, avoid p-hacking, avoid harking, avoid all these researcher degrees of freedoms, avoid misinterpreting what p-values are, avoid all of these misconceptions of null hypothesis significance testing that we talked about beforehand. Okay, I've color-coded these in such a way to show kind of the different camps. Okay, the green here, these are things that we all need to be doing and that don't really deal with the statistics themselves. Okay, so registration, sense, these are things that we all need to be doing. We've got this one camp that adopts the new statistics. Okay, these are the things in red, and then we've got the Bayesians, and that's the purple. So we've got some different camps. We've got people that are really big into null hypothesis significance testing. We've got this new camp of people very interested in meta-analyses and confidence intervals and effect sizes, and we've got the Bayesians who are off doing their own funky thing. Okay, so there are problems with null hypothesis significance testing. Doesn't mean that the system is completely broke, but we need to be cautious about our interpretations of our results. Okay. In the next lectures, we will talk about confidence intervals, effect sizes, meta-analyses, and power. Okay. Hope you guys have a great day, and I will talk with you later. Bye-bye.